In part 1, let us now consider the applications of some of these logic gates. The first logic gate which we are going to look at is the AND gate. And we are going to look at the AND gate as applied, that can be applied in a seatbelt alarm. You would have noticed in some of these new vehicles that once the occupant has not tied the seatbelt and the vehicle is moving, it will show an alarm on the display that the occupant needs to tie a seatbelt, and sometimes it will create an audible alarm to make a sound. Now, the way it would work is, remember, the AND gate works by giving a high output whenever both of the inputs are high. So in this case, the conditions that we are looking for is if the occupant is seated and the vehicle is moving, then the car must ring an alarm. So in this case, we'll say if you have you have two inputs, the ignition switch and the seatbelt. So if the ignition switch is on, that is the vehicle is about to move, and the seatbelt is unbuckled. The seatbelt is unbuckled, which will be represented by a high. Then we want the alarm to go off, right? So what the system will do is it will look at the ignition switch, possibly through a certain timer, to say after 30 seconds of the car engine running, it will make sure that after 30 seconds of the car running, while the car is still running and the seat belt is unbuckled, then the alarm rings off. So this could be an application of an AND gate. The OR gate, on the other hand, or the OR gate, or the OR logic function per se, can be applied in an intrusion detection system. If you think of a home alarm. So the way it will happen is it will detect if either the points of entry, which will be the windows or the doors, are open. If the door is open or a window is open, then the input to that particular sensor would be high. So in case either of them is high, then the alarm circuit will raise an alarm to alert the owner that the house is vulnerable to intruders. This would work because the OR gate output would be high whenever either one of the inputs are high. The last example I want to give is an example of a NOR gate which can implement an industrial mixer. In this case, we have a setup where we have three ingredients, ingredient 1, 2, 3, and these ingredients, they are being connected to our logic function, which drives a power converter with a high signal. So the way it operates is each of the ingredient bottles will have a sensor which will be triggered. It will have a sensor, and another sensor. So the sensor is triggered to output a 1 if the level of ingredients reaches beyond the sensor. So in this case, it will detect that the ingredient is about to run out. So typically, all of the sensors will be 0, 0, 0, which means then if they are all full, it's 0, 0, 0. Because this is a NOR gate, then the output will be 1. That higher output will switch on the power converter here. So this would be on, and the power converter will continue mixing your favorite juice, manufacturing your favorite juice. The moment one of the ingredients run out, let's say this particular ingredients, then this would be a high because the sensor will detect that one of the ingredients will have run out. Then the output will be high. Now, once one of the inputs is high, which might be this case in the truth table, then the output becomes 0, which means now the power converter becomes off. And the mixer stops working because now one of the ingredients have run out. All right. Now, moving on to waveforms or timing diagrams. One way of looking at the operation of a logic circuit, or one way of debugging if you're constructing a logic circuit, is to look at the timing diagram, how it behaves as the input and output changes. So in this case, you have the inputs, A and B, which will be changing depending for each and every time slot. So you have time slot 1, 2, 3, 4, 5, 6, 7. The inputs are changing. And you can know if your logic function, in this case, we have a NOR gate, it's working properly by verifying the inputs against the output for each timing slot or for each period, however you want to call it. So in this case, if you look at period 2, you will see that the input A is 0. Sorry, the input A is not 0, but it's 1. You will see that at time period 2, the input A is 1 and the input B is 0. And because this is a NOR gate, look at 0, 1, this corresponds to this particular row. It means, therefore, then our output will be 0. So in this case, in fact, if you have a truth table, you can construct all of these timing diagrams output just based on the truth table. Another example that you might take is time slot number 5. Time slot number 5, you have a 0. You also have a 0 coming into the logic circuit. And you will see that then it means this is the first row of the truth table. Then it means then our output has to be 1, which is what you see here. Looking at a different example, you might have these two other logic gates. Remember, this is the exclusive NOR gate and this is the exclusive OR gate. So the exclusive OR gate, remember we said the way it functions is, this is the symbol, but the way it functions is it will give you a 1 whenever the inputs are equal to a 1. So if you look at the way, if you just focus on the exclusive OR gate, you will see that when you have 1, 0, you have a 1 here. Whenever you have 1, 1, because remember, this plus that is not a 1, this will give you a 0. Whenever you have 1, whenever you have 0 plus 1, this should give you 1 because 0 plus 1, they are equal to 1. It gives you 1. When you have 0 plus 0, then you have 0. When you have 1 plus 0, it will have 1, and so on and so forth. So then you can, given this set of inputs, you can be able to then complete your timing diagram for the XOR. Then obviously the XNOR gate then becomes the opposite. This one becomes the opposite of the XOR gate.